you know what that is? No, I don't know. So what's the need? What's the problem? What frozen down a set? Yeah, frozen down. Interesting. Usually for a product, I think that the heat probably like some kind of is diverse. Okay. He said that he only allowed two characters. Or functions this again is not okay, but it doesn't affect mathematics too. I think it covered it most all the subject. Oh, I feel. Oh, you didn't follow the no, I haven't followed the news since December 5th. I decided to follow the videos. But you didn't find me. No, I just got something. Yeah. Okay. So now the entire and it's a budget is short. Wow. So, but some people did get the success stories. Like this guy, Roboski got on a success. Yeah, I just got this. Not you really get that. So, I'm real that, but the one will not be coming. And later, when you come in later. Oh, I didn't. Seriously. I was wondering about I needed to know my passport. So I sent it to the opposite job. I was wondering that. No, can you passport? That's not the problem. Yes. Because if there's some disruption of it. Yeah, I did it well. Because I was worried that because it was like forever. Also another protocol. That's right. Also part of this and some money. So year after year, how was just everything frozen in France. Wow. Here I'm having a college situation. Yeah. Yes. See what to say. The world on a day. Like what she said, Yes, so you have Timothy Logvinenko, Cardiff, speak about is it the space.
So, firstly, let me thank organizers for inviting me here. It's always a great pleasure visiting PMU. My first visit to PMU was when this building was not yet finished and everybody was living in pre-house. But every time I came back since then was a huge amount of fun. So secondly, let me say from the start that I'm very scared to give this talk in front of Nakajima-sensei. So if anybody has any difficult questions, please ask them to Nakajima-sensei. He'll probably give a better answer. Lastly, let me explain this. This is actually last page of my notes. But if you've heard me giving math talks, you might have noticed that I always have this problem. I deeply believe that the results are not as important as motivation for them, are not as important as the answer to the question, why did you try to do this? So I run my talks as a story with the results being the last part. Usually I run out of time. And I end up not actually talking about my results, about motivation results. So for this, I decided to write basically the main results, the last page of the notes there, just in case I don't get there. At least it would have been on a sort of blackboard to start with. And now I'll start the story from the beginning and hopefully get to here, and more importantly, as to why would you sort of bother with that. So this is not which we had already started. This is insurance sort of eventual goal to get. So why? What is Heisenberg algebra? Yeah, everything here is joined with Adam Genge. So, well, I believe the origin, the finite dimensional version of this arises in quantum mechanics. But the first thing, first generalization that one can consider is what's called an infinite dimensional Heisenberg algebra over a field. HA, where A is space probably want it to be heuristic 0. Just in case. So let me start by saying that these definitions are usually given as Lie algebras, but for the reasons of that I work with stratification of things in the end, I prefer to work with regular algebras. So all the definitions I give will be universal enveloping algebras or the corresponding Lie algebras, where we identify central charge with the unit of the algebra. So we mod out the central charge element to be 1. So with that in mind, the generators of this graph are elements we call AN or ON in integers, and we have two relations. One essentially says that the central charge element is 1, and the other is what's called sort of the famous Heisenberg relation. And that would be the commutator of AM and AM is the delta function of n and minus m, so they commute unless the two numbers are inverses of each other, times m. So why would you want to think of something like this? Well, this algebra is isomorphic to the ring of differential operators on infinite on polynomial ring in infinite number of variables. And to see this, you map a minus n to differentiation, partial differentiation in x10, and a n to n times x10. And a 0 sort of to 1. And then this relation is simply a differentiation of product. So yes, this is for positive n. So I want so my negative sort of a's to be differentiation, my positive sort of a's to be also right. So then we have Fock space representation. F, which is in this can be thought of as just the polynomial, just this infinite dimensional polynomial ring with HK acting via these identifications. Now, and of course, you can just obtain FK by taking HK and filling all the A minus numbers. So basically, it's the sort of the positive part of this, which is this representation is rather important. This story, it's reducible, faithful, so. So next thing to consider, and this definition I've sort of read in about the Hilbert schemes of points of on surfaces, and this definition essentially systematizes the result about action of Heisenberg algebra on homology of Hilbert schemes of points in the surface, the famous result by Logvinenko and Ian Granovsky, which we'll talk about next. So first I will so think of this generalization of this definition as a language necessary to formulate the result, which will be in the next section. But if you sort of start thinking about this, you will arrive to the following definition. So we can define Heisenberg algebra whose generators are parameterized by elements of a vector space with a bilinear form, and we need this bilinear form to be symmetric. And sort of getting rid of this assumption being an important part of this story. So the generators now are same is indexed by integers, but now they're also indexed by elements of our vector space.
But you already have them too.
So
You already have them here.
well, yes, this will be the sort of the proper definition, but this is the sort of a different definition for a symmetric kind. And sort of that's the definition we wrote, and it might take. I want to convince you that this is the right definition. So first, I'll give this sort of well-known definition that there's and you can see the difference between this and sort of if you want to look ahead, you can see what this will actually turn. So generators and relations work like this. We still have the central charge relation. The zero things are always, I think, always one. And we have the linearity relations. Equals AV plus AW. And a scalar multiplication. If you multiply vector by a scalar, you're just multiplying the generator, corresponding generator by scalar. And then the Heisenberg relation, and this is where the bilinear form comes in. Looks like this: the commutator of AVM and AWM is again delta function minus m. They still commute less numbers are inverses of each other, and we still have m here. Now we also have the linear form. Now, if you swap these two things around, then this m here will change sign, but this will become WV. So this needs to be symmetric for this definition to work. And as before, we define the corresponding Fock space as the quotient of this algebra by where we here for the negative generators, negative index generators. So this, as I said, I thought of this simply a language which describes what happens in a rather beautiful sort of geometric action of I mean this Heisenberg algebra and the rather relations between them. Other relations which exist between certain sort of operators on correspondences, on cohomologies of Hilbert scheme of endpoints on a small projective surface for various things. So this is the Nakajima, Granovsky, Heisenberg, Hochschild. Mid-90s. Now, at this time, I was an undergraduate student in Cambridge, and there were people running around saying that, this guy in Granovsky, our lecturer, has proved something very cool. And some Japanese blog called Nakajima sort of proved the same thing. So I tried actually to look at both papers as I think, third year undergraduate, and got completely lost and gave up. Never sort of expected that one day, this maybe out this story. So this story goes like this. You have which is a small projective surface. And x square bracket m will denote Hilbert scheme of m points. So a scheme parameterizing intervals of points on x. Or rather, sub-schemes of x of finite length n. So if you do this properly, then by allowing this sort of thick neighborhoods of points, you will get smooth resolution of a singular quotient of xn by the natural action symmetric group. So what Nakajima Sensei and team proved is that if you take the Heisenberg algebra of the rational homology of x, then this will act on direct sum of homologies of Hilbert schemes once. Not only that, this action identifies as a representation of this algebra. This is just the Fox phase. And the way this was done is that they constructed for each of those generators correspondences on the products of the Hilbert Hilbert schemes of points, which by the usual push-pull gave the maps between homologies, and then they proved that these correspondences satisfy those relations. So I mean, so from the start, if you look at those papers, these were defined by geometrical objects on products of these guys, and it sort of indicates strongly that this should live to the right category there. So, however, this seemed to be very much a surface story, because when x is not a surface, then this is no longer smooth, and this is sort of very nasty object with small endpoints on x, which wasn't sort of promising for getting something like this. So the sort of a hint as to what to do. The following theorem, which was proved, well, it's actually a combination of the theorem proved by Hyman, but it was essentially application of a theorem by originally came crazy. Hyman So sometimes it's written in literature as Hyman, Bridge, and King Reef equivalents. So this is around about here 2000. And it says that if it's a small projective surface, then the derived category of the Hilbert scheme of n points on X is equivalent to a select invariant derived category of n product of X with itself n times. So this is a invariant derived category. But if you've got an equivariant derived category, that means for an action of a finite group, that means that you're just considering the usual derived category of the quotient stock. So I view so the key insight that you should consider n symmetric product of X as a smooth stock. So don't consider this nasty singular space over there. Consider the smooth stock. And working with that for surfaces is exactly the same thing as working with Hilbert scheme of endpoints. And this seemed to be like a good way to generalize the story away from the surfaces. So this gets immediately. For any projective X, one should try and lift the Logvinenko action to the action on the derived categories of the symmetric quotient stocks. And there was some progress made in this direction, particularly the final and very nice work on this was a work by Krug in 2015, which more or less does this. But so Krug, so this was done by Krug in 15. But the problem somehow is that Krug just leaves this on level to level of derived categories, not on the enhanced level. And doing this on enhanced level is crucial for additive invariance. So this led me with Clemens Koppensteiner, student of Sabine Kautis, and Adam Genge, who was also a postdoc in Oxford with Clemens at the time, to try to lift this story to the enhanced categorical. And the result, when I give a talk about this result with Clemens and Adam across 5 blackboards, this and to cut the long story short, if you also want how to work enhanced here, you will in the end arrive to this. I mean, not just enhanced, but if you want to do it sort of, if you want to do this properly. So what we have are 2 categorizations. Of the Heisenberg algebra. So this is Hoffensteiner. And myself in 21. But it's very important to sort of to write three fundamental works which inspired us, which is Kovanov in 2010, who first did this two categorification, but essentially for X being just a point. So he categorized the original Heisenberg algebra, which was parameterized, which was not parameterized by anything, in the sense of it's just the Heisenberg algebra of spec K. So then there was Countess Likert, who took Hovanov's calculus and understood how to lift it to resolutions of ADE singularities. So they're very specific, from point to a surfaces, but to very specific surfaces. And then Krug in 15, who did non-enhanced, but the Nakajima Heisenberg action with the quotient steps. So by doing this properly, I mean, means doing this in a natural way on DG level and working with sort of algebraic variety on a DG level is it can be always enhanced by smooth and proper DG category. And we decided that instead of saying let's take X and then take a DG category which enhances it, let's from a start trying to do it on a non-commutative level. So this is sort of a non-commutative equivalent of a smooth smooth projective variety. Any smooth projective variety can be enhanced by smooth and proper DG category. In a certain sense, if it's DG enhanced and it's smooth, if it's smooth projective variety, then the DG category has to be smooth and proper. And so we start with this DG category. For specialists, we immediately replace it by category of perfect modules, which doesn't change the Maritic modules class, but gains by work of Shklarov the homotopy Serre function. So if you just take sort of, this can be taken to be a smooth and proper DG algebra, and that doesn't have a sort of Serre function on it. If you replace it by perfect modules over it, so what we do, we construct the following in that paper. So first thing we construct is the categorification of the Heisenberg algebra of this in a sense, which is the constant triangulated Heisenberg two categories. Two category HV. So again, if I'm to be sort of very precise, what this is just sort of what this technically is a bi-category enriched or homotopy category of DG categories. In other words, the one morphism category is a DG category, but the composition is only a quasi-function. This is because we construct this as a Drinfeld quotient, as monoidal Drinfeld quotient of a simple strict DG2 category. And monoidal Drinfeld quotient we all to Boris Shoyhead, and unfortunate unfortunately, when you apply it, what pops out, even if you started with a nice DG2 category, what will pop out is by category reached or how category of DG categories. So to describe this, unfortunately, I already gave a talk on IPMU, which sort of went in detail as to what this is. For the moment, let me just say that objects are just integer numbers. And you will see in a moment why they are integer numbers. And one morphism categories. So usually when people categorify, they categorify things not about a two category, but only by monoidal category. Monoidal category is a two category with a single object. But since we're going to be acting on symmetric quotient stacks, which are indexed by positive integers, it sort of makes sense to do this. And one morphism categories are defined via Kobanov style diagrammatic calculus. So this will be running ahead in the story a bit, but objects in here are essentially in the simpler category that this is a sort of quotient of. The objects are just free words on symbols P and Q indexed by objects of this category. And the morphisms are certain diagrams, which so a typical things would look something like this. So I mean, this will be indexed. So this would be like A, B, C. This would be A, B, C, D, and D. Let me forget. And then the rules are that you can run a string from P's to P's, strings run up, from Q's, strings run down. So in particular, you can have a string which runs down from a Q and then up back to P, giving you caps. Unfortunately, this also means that there can exist any number of these buttons. So this is very much not a home finite category, which caused us a little. So, and then once you do this simple category, you take a perfect hull of it, and then you actually consider modules of this. You consider twisted complexes and so triangulated hulls quotient out by direct summons. Also, sorry, triangulated hulls, and then you allow direct summons in as well. And then you take Johnson quotient by things. So, but in any categorification, the idea is that the algebraic categorifying should sit inside appropriate additive invariant of your two category. So these correspond to certain alternative generators of Heisenberg algebra, which I'll talk about.
So what are indices? Are they objects?
Well, indexes objects in the category. Moreover, yeah, in this case. Moreover, what I haven't said that actually if you have a morphism, if you have morphism in your category, you can label a string by this morphism, and then it has to go from PC to PC dash. So any morphism allows you to sort of change the indexation of the object the string goes on. So string without any indexes, indexed by identity morphism, so moves from A to Z. So it's like I said, I will spend the whole talk explaining this trinket, so there's really no and then we also now this we really construct, and there's a little hard work goes into this. But this, so we construct the Fock space representation too far. So the categorical Fock space for this turns out to be a perfectly natural object, which is actually described in terms that of the two category of enhanced related categories that Rina talked about. So the Fock space presentation Well, sorry, two functions. Too far. So this is a, I mean, it's not a sort of it's what's called a homologically strong two function. So it only satisfies the usual conditions of two function up to homology. And this is, we call it phi v. And it goes from our two categories to a very nice to the what we call categorical Fock space F. And this is, thanks to Rina's talk, is quite easy to describe. This is this guy is one subcategory of the Rina talked about the big version. There is also a small version of this homotopy bicategory of enhanced triangulated categories, where we consider the ones which are currently complete. So let me continue writing to explain what I mean. Supported on the symmetric motion stacks. So what happens is the proper definition of this is a two category whose objects are integers again. But now I think of negative integers as just sort of zero categories. And for positive integers, I think of them as as a category SNV. So so by identifying both negative integers with zero and positive with the symmetric motion stacks, I then my one morphism categories from sort of n to m are just enhanced functors in here from S and V to S and V. So the reason this is done is that so then now therefore each sort of one morphism in here from n to n gives me an enhanced functor from n symmetric motion stack to n symmetric motion stack. And I'm going to sort of so this so this trinket. The point, why are we doing this? Why are we doing this hugely complicated thing? Because in a sense, if you sort of read papers by Toa and particularly by Gonzalo Taboada, he will talk about universal sort of motifs. These enhanced DG categories, the Marita category with enhanced DG categories is in some sense universal motif category. Anything sort of you want to build any relation between any additive invariants should exist here. So the advantage of doing this like this is that you can decategorify it using any sort of additive invariant you care about. So in the paper, as it is traditional and as we were sort of told to by Hoganov, the exception list, we decategorified using the numerical graph group. So numerical group is just the usual K theory, usual K group, where you factor out by the kernel of the Euler form. So all the things in which Euler form you evaluate to zero on either of the sides, you just set to zero. So in particular, on numerical K group, Euler form is non-degenerate. So we construct this, and then we decategorify it. Using numerical graph and group. And I promise that once I draw the next diagram, it might really become clear why did we bother with this insane categorical constructions.
For surfaces, there are the symmetric powers of surfaces, right?
Not surfaces.
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 I'm saying for surfaces, there was symmetric. So for high dimensional variety, is it also symmetric powers which you can of categories?
Or yes, it takes symmetric power of the corresponding digit. So this is yeah. So when I say this, I mean a very specific thing. I mean there is a way to define a sort of semi-direct product of your original digit category and the symmetric group, where you sort of you index every morphism by permutation. So when the category is just an algebra, this is the usual semi-direct product of a group and an algebra. You can extend it to a
It's like tens of power.
sorry.
Some kind of external tens of
Oh
product.
yes, sorry. Of course, I said acts on the end. Yeah, you're completely right. My apologies. So this thing has a property that derived category of this S and V tensor is just is the same thing as Sn equivariant derived category of V tensor. So in your sense was Gardner, but so in the paper I actually described this formalism because I like working on the Morita level. So in a sense, you made this definition by explaining that objects here are somehow objects in here with an action of a set. And I define somehow a category whose just ordinary modules over which are just in a clear way equivalent to a module in here with an action of a sense. It's sort of neater to deal with for phrases. So what do we mean to decategorify? To decategorify is means that you choose your favorite numerical invariant, for example, SK0 and now I take the Heisenberg algebra of the numerical Grothendieck group of P. So this has an Euler form. Now I'm cheating a bit because an Euler for a general variety V, an Euler form on its Grothendieck group is not symmetric. And also this is not a vector space, this is a lattice. So in a moment, I'm going to tell you what definition did we use here. But there is a definition which makes sense. So I'm just going to give it in about 5 minutes. And then you take a Heisenberg algebra of our non-commutative variety. And the key for decategorifying is to construct a map pi to the numerical Grothendieck group of our categorification. I mean, of course, pi should be an isomorphism. We usually say that this categorifies this if there is an isomorphism between this algebra and the sort of numerical Grothendieck group of your two-category monoidal. So we were only able to show that this is injected. Actually, original Hovanov's paper, who defined this categorization for a point, so for a case where this is just one-dimensional, so when this is just K, he also was only able to prove this map to be injected. It then took a 60-something page paper to show that it's actually surgeon. But now the importance of this guy becomes clear, because whatever additive invariance you choose, for example, K nu, this means that this two-functor, sort of categorical two-functor we did, induces an action on numerical group on the slightly wrong, on the direct sum of K0 nu of Sn because these guys, this FV, the one morphism categories are enhanced functors between these S and V's. So anything in here maps to an enhanced functor, and then we just look at as to what does it do on the level of numerical. Now then there is a standard trick. So how did we actually prove that this map is injected? There's a trick which says that we have phi v, we constructed this map pi, which we know nothing about. But then, by constructing this map pi, we now have an action of the Heisenberg algebra of the K theory of T on this thing. And when you look at the vector sort of at the generator of S0V, so at the generator of the 0-degree part of this, you see that that all the negative sort of non-Fock space operators act by 0 and 1 acts by 1. There is a very easy lemma which says that if this happens, then there is a copy of Fock space representation sitting in here. So by sort of representation theory tree, we also obtain a map from the Fock space of this algebra in here. And we know that this map is injected. When I say copy sits here, it's really is injected. And this is the sort of standard option. And now, of course, the trick is that this map has to be injected, because if it's not injective, then this group acts, Heisenberg algebra acts faithfully on its Fock space. So it could not go through a non-injective map and still act faithfully on everything here. So actually, this is the same trick used by Hagen, Fogonov, and everybody in this business. If you construct an action of Heisenberg algebra, just look at if there is a copy of Fock space sitting in here, because it obviously does. Now, in particular, this constructing this map, this sort of decategorifying map, now gives us the following thing. It gives us what we hoped at the time to be equivalent of Nakajima-sensei's action. Observe, I now have the Heisenberg algebra act on the K theory of all symmetric quotient stars. So this lifts, our hope was that this lifts Nakajima-sensei's action from Hilbert schemes of points of surfaces to any non-commutative smooth projective variety. Of course, there are a number of issues. For example, actually showing that we get the same action. So, a couple of unfortunately, we soon discovered that this was a wrong choice of decategorifying integers for a number of reasons. Firstly, numerical growth in a group sits in the algebraic part of the cohomology. So, if you wish. And therefore, we do not get action on the sort of rational homology or even complex homology with these guys on a very small part, or on a very small algebra. So, but things get even worse. So in a sense, we don't get full action by Nakajima and Granovsky. We get just the small piece of this action, but it gets worse. So we prove the following proposition, and we're very happy with ourselves, that if this map is actually surjective, which would show that indeed this doesn't just contain a Fock space, but is the whole space. Also, sorry, it's the other way around. If this categorization map is isomorphism, then so is phi. Which means that if we can prove this to be isomorphism, then this would automatically have to be the whole of the Fock. This would have to be the whole of the Fock space. Sorry, Fock space would have to be the whole of this. But unfortunately, numerical rectangly broke as one nasty bar. The Euler formula doesn't hold for it. The numerical growth in a group of a tensor product of VNW is not the tensor product of the corresponding numerical growth groups. Now, the thing is, this unfortunately allowed us to find a very easy counterexample to this being an isomorphism. So phi is not an isomorphism already for the enhanced triangulating category being deep epoch of an elliptic curve. So already for elliptic curve, so what's the problem here? The thing is that this is a rather nasty sort of non-finite category. But everything here is, when you restrict to appropriate graded part, you know exactly the dimensions. Because up to parametration, this is a free abelian group. It has a basis. Then for each element of this basis, you get all this sort of positive and negative things, but we're in the Fock space, so you just have all the essentially you have a ring of symmetric sort of symmetric monomials for each element of the basis of this. So basically, the dimension of this is very easy to understand. And if you look at it, you realize that unless Q-not formula holds, this thing will be bigger than this. The only way is, in fact, statement. If the Q-not property holds for powers of V, if K0 num of V tensor V is K0 num of V tensor K0 num V, then this is an isomorphism. But of course, this already fails for elliptic curve, and we go there explicitly. And that means that also this is strictly bigger than homology. It's not a problem. Just means that our Heisenberg algebra somehow sits inside it. There is an interesting question as to what happens. So what is the extra, which is not part of the original Heisenberg algebra, but so understanding this led us to understand that we should have chosen an additive invariant, which is which the Q-not formula holds, because then we would immediately have this being an isomorphism, and there would be a strong sort of hope for this being. So now I'm getting closest to why we have to do all the strange things on that board. So quantum. Deep category file. Using Hochschild homology. So, Q-not formula holds. So phi would be an isomorphism. There is a small technicality there. There are two pieces you need to show that if the Q-not formula holds, then the fact that this isomorphism follows from a certain sort of formula proved by Baranovsky for the decomposition of the sort of which gives a certain decomposition of a symmetric quotient for in the geometric case when V is actual variety. But for an actual symmetric group, it's quite clear what that should be for a non-commutative case, and we are working on grouping. So modulo that just Q-not formula holding homology is enough. This is the full space, but even it's nicer when V is d before of a smooth projective variety, then the Hochschild homology is the same as complex homology. This is so-called HKR isomorphism, also, although in this generality, I believe it's sort of original idea of Alexei. The Hochschild, the Hochschild constant Rosenberg isomorphism is in its classical form described as a certain isomorphism in affine case which identifies this with differential forms, which which can be generalized to X and its algebraic Durango homology, which when the field is the complex number, it's just the same as this, but more current. In particular, this means that if I replace on this diagram K0 num by Hochschild homology, I will get here the whole of the complex homology. So I will extend so the action that pops out of it, the Heisenberg algebra, will no longer act just on the small part, algebraic part of the homology, but will act on the whole complex homology. So there we are really getting close to generalizing Nakajima and In's result to all these non-commutative varieties. However, so this was us about half a year ago. And then we realized that we sat down to try to generalize this to Hochschild homology, and then we ran into problems. The main problems is that Hochschild homology is a graded vector space with a non-symmetric bilinear form. And it was there was no definition of the Heisenberg algebra in that generality. So I gave you a definition of Heisenberg algebra of a vector space, non-graded vector space, with a symmetric value. Now, this also was not definition we wanted to use, because we built our two-category verification around a different set of generators. So let me explain this. And this definition really exists only for lattice. So let me now go back to Heisenberg algebra. So at this point, you need to answer a question: what is a Heisenberg algebra of a graded vector space with a non-symmetric linear form? So first, let me tell you what the Heisenberg algebra of a lattice is. So you will have a lattice, but now chi can be general, not necessarily symmetric. So what do we have here? We have a lattice. So M is a free abelian group. And chi is a map into some integer value by being a form. Then so the thing, to my knowledge, the first people who thought of using these generators, or rather necessarily using them, were Countess and Likata in their lift of Kovale's work to resolutions of AD singularities. Because they realized that A generators in a categorical game do not have an easy sort of description, while somehow, which I have time to explain why, these generators are very easy to pinpoint what they should be in a categorical function. So now the generators are P and Q sort of elements indexed by elements of my lattice and positive now integers. And you could think that this is just sort of positive A's and negative A's, but that's not quite the case. This will become clearer very shortly. So the definition I give you is a definition from our paper with Adam and Clemens. It follows the ideas of Krug and the ideas of Countess and Likata, which define it in a very sort of special cases. The full definition I believe. So the relations. So the central charge relation, so this the zero index things should still be 1. So the very and then just like in the A generator definition, it follows from the Heisenberg relation that positive A's and negative A's commute with each other, then P's and Q's always commute. So PVM PWM equals PWM PVS. And sort of same for Q's. So in order to save time, I will not write the two versions of these relations that are identical. And then the problem is that these P and Q generators, they're no longer linear. In the parameterization of the by elementary lattice is no longer linear. So what we in fact have is the following: Pn of V plus W is you take a sum over.
Isn't it written there?
Sorry?
Isn't it written there?
Yes.
And maybe I have 2 minutes.
Yes, just a second. So let me write this because one definition from there is missing. So and then I will just explain this more. So and then so this is a nonlinear. It's sort of all part, not just PVN and PWN, but also the intermediate products where the powers are to n. And now I'll also tell you how to commute Q plus 3. Here, the formula happens. You take a sum of time from 0 to the minimum of m and n, and then we have a certain index which I explain in a moment. And this index is a certain function of the form evaluated in P and W. And then you take you've commuted, but you also depend. I tells you how much their powers drop. So it's P m minus I will V n minus I. So now, what's SI? SI is do I have it written here? No, I don't. So SI of any number x is defined to be the binomial coefficient x plus I minus 1 over I choose x plus I minus 1. When x is a positive integer, then SI of x is the dimension of the I-symmetric power of complex vector space of dimension x. And when x is negative, it's the dimension of the alternating power. I-alternating complex vector or corresponding complex vector space. And then we just apply this to the. I don't have. Can I have 5 more minutes to finish the talk? 5. Yeah. I'm not going to write anything.
The same thing.
So the story of these generators is that basically these guys are exponentiation of A generators. If you write a generating series of A generators, so take sum of A n over n c to the power of n.
It's so difficult now. People all saying yes.
All right. So if you take the generating power series for strictly positive and strictly negative A's and exponentiate them, you'll get the generating series for P and Q. However, that tells you that P's and Q's are also generators. But then you suppose, and it's not very difficult to show that these are the relations they have to satisfy. In order to prove that the two definitions are equivalent, you would have to show that they satisfy no further relations. You also have to generalize this away from a lattice to a vector space. And that means coming up with a scalar multiplication relation. So this is the state of things before we got there. We had one definition for vector space for A generators, which required the form to be linear. We had another definition for P's and Q's, which could only work with lattices, but did not require, not linear symmetric, but did not require the form to be symmetric. We needed sort of this definition, but we also wanted to understand the relation to A definition, because this is what sort of categorification is essentially wired up. So after a while, we managed to find the missing relation, the scalar multiplication relation in QQs. That's a pretty sort of hard combinatorial formula. You sum of all partitions of M, you take the multinomial binomial number, where from Z you choose Rn is simply a collection of R1n is number of in a partition of n parts of size 1, R2n number of parts of size 2. So you take all these and then you sort of take this multinomial coefficient. So that's what appears here. And then you just PV to the power of some partition. It's just PV to the first element of the partition. So and then we also managed to, inspired by this, we rewrote the A generator definition in such a way that it's no longer requires chi to be symmetric. Basically, commutation of strictly positive commutation when M is not equal to M. And this Heisenberg relation should be separated into two. Then by specifying it's minus n and n, you sort of break the symmetry. But then the question is, why would these two have anything to do with each other? So then we proved three theorems. Firstly, if you choose something to be a basis, then you can restrict your generators to being parameterized by elements of the basis and forget about these linearity relations. And here, forget about these relations. This is called reduction to basis tree. That made everything finite dimension and allowed us to actually to prove that the definitions are equivalent in completely general cases. So after you exponentiate, there's no further relations between P's and Q's. And finally, it's a very cheap trick, but from when we wrote down this definition, we realized that actually it's completely independent of the bilinear form as long as it's non-degenerate. So it's a one-line proof. I will not trouble you with it now, but if you take any two bilinear forms on the same vector space which are non-degenerate, the algebra you get will be the same. So there is really something called Heisenberg algebra of vector space, which is independent of which.
You could take chi symmetric,
I think I got that form to be symmetric.
which was already known. And this case was already.
Yes. After you go.
All right. Thank you very much. Any questions to speak up?
What is this lattice? Is it topological K theory?
Latest what?
I mean, you need some lattice, right? You started from a category, then you need.
No, I don't need a lattice. That's the point. There was so the definition of Heisenberg algebra of a lattice existed because we needed we decategorified using numerical Grothendieck. And that is a numerical Grothendieck group is a lattice. But then the problem is that we only define this for a lattice because the sort of the scalar multiplication relation, the additivity relation is sort of difficult, non-linear, but not too difficult. The scalar multiplication relation, so to move from lattice to a vector space, that required some very nasty computations. Now it's done. Now we know what it is. We can define sort of P and Q version of the definition. We can describe P and Q generators for Heisenberg algebra of any vector space. So there's no particular need to use lattice. I know there is a very interesting question of finding a lattice inside the Hochschild homology, which is probably what you meant. Well, we very much don't try to do that. The Hochschild theory is sort of we avoid that.
Or the questions. If not listening, speak again.